Hey everybody, it's Ripley back again, talking about 8.2. We're going to talk about series and infinite series. Most, I guess, is not really an and. It's a sort of parenthetic. We're going to talk about series and infinite series. All right. Now, hopefully you remember this from pre-calculus. If you remember from 8.1, what we have is we have a set. We have a box. And in that box, what we stick is a list of ordered things, right? And then we get a sub n from some rule. I don't know, -1 to the n minus 1 times 2n over n squared plus 3, right? I stick n equals 1n, that becomes the first term. N equals 2, that becomes the next term, etc., etc. All that a series is I hate that, is a series, or excuse me, a sequence, this term, this a sub n, with a sum in front of it. So all we're doing is we're going to take the sum from n equals 1 to infinity, if we're talking about an infinite series, of a sub n. So instead of just creating a list like we did with sequences, a1, a2, a3, dot, 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 right? And this thing goes on forever. What we're going to do is we're going to add up a1 plus a2 plus a3 plus dot, 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 all the way to the end. That's called a series. Ta-da! And that's all you need to know when we're done. No, just kidding. All right, now let's talk about this. First thing we need to talk about is something called a partial sum. Let's talk about partial sums. All right. Now think about this. I'm going to have a partial sum, which the first one's going to be s sub 1. And all that s sub 1 is a sub 1, which I guess I could think about this as the sum as n goes from 1 to 1 of a sub n, right? And then I've got s sub 2. And this is going to be a sub 1 plus a2. Right? So again, we can think of this as the sum as n goes from 1 to 2 of a sub n. I won't do that anymore. I know that drives you guys nuts. S sub 3 is a sub 1 plus a sub 2 plus a sub 3, right? Now, let's be really careful here because there's a cool little trick. Do you realize that s sub 2 is actually, if you think about it, it's s sub 1, right? Excuse me. It's Sorry about that. Wait a sec. I'm getting a little bit ahead of myself. Let's back down just a sec. This is a better example to use. Notice, this is s sub 2 plus a3, right? So I can write s sub 3 as s sub 2 plus a3. True? S sub 4 is a1 plus a2 plus a3 plus a4, which is equal to s sub 3 plus a4, isn't it? So it's kind of this iterative process, right? Now let's write s sub n a couple of ways. S sub n is a1 plus a2 plus a3 plus dot, 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 plus a sub n. This is a finite sum. I could also write this as what? Well, the term immediately before a sub n is a sub n minus 1, right? And if I add a1 plus a2 plus a3 all the way up to, this is a1 plus a2 plus a3 plus dot, 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 a sub n minus 1 plus a sub n, right? So s sub n can also be written as s sub n minus 1 plus a sub n. Now there's a crafty little algebraic trick that wink, wink, nudge, nudge you might be able to use down the road. Look close. Do you agree that a sub n can always be written as s sub n minus s sub n minus 1? So if you happen to know these two sums, you might just be able to pick up what a sub n is. Now think about this. If s sub n is equal to a1 plus a2 plus a3 plus dot, 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 plus a sub n, and I want to figure out what this series is as n goes from 1 to infinity of a sub n. What's another way that I could write that? Because I know that's a1 plus a2 plus a3 plus forever. So how can I link these two guys together? What am I doing in this case that I'm not doing in this case? Well, I'm not stopping here. I'm stopping at n. So if I want this guy right here to never stop, what should I do? Just let n go to infinity, right? So another way of writing this is the limit as n goes to infinity of s sub n. They're identical. There's no difference. Piece of cake. Nothing to it. Okay? Now, we're going to have some fun now. This is where we start getting crazy. We're going to talk about convergence and divergence. Divergence of infinite series. Infinite series. But before we do that, I want to hem and haw just a little bit here. All right? In kind of standard position, remember when we wrote the quadratics as ax squared plus bx plus c. That's a quadratic in standard position. It's in standard form. In standard position, series look like this. But there is absolutely no rule that says that you have to start this thing at 1 and finish it at infinity. If it's a finite series, I can start it at 1 and finish it at 17, or I can start it at 5 and finish it at 38. That's still a finite series. But what happens is, if I start changing n, then a sub n changes as well. And I'll give you a couple of examples of that here in just a sec. Okay, so let's go ahead and start talking about convergence and divergence of infinite series. I think a lot of students, when they hear about an infinite series, are like, wait a sec, I'm adding up an infinite number of things. How could I ever converge? How could I ever go to a number? Well, if you think about it, remember this guy? If I take 1 plus 1/2 plus 1/4, hopefully you remember this from pre-calculus, and you've probably seen it before if you haven't, plus dot, 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 plus, now what is this? This is 1 over what? 2, and then this is, so each one of these is the power of a half, right? This is 1/2 to the 0, this is 1/2 to the 1, this is 1/2 squared, etc., etc. Now think of this. This is n equals 1, it's my first term. This is n equals 2, this is n equals 3, etc., etc., right? So you can start seeing a pattern here. What I have is 1/2 raised to the n minus 1, because when n is 1, I got 0, which gives me 1. When n is 2, I get 1, which gives me a half, etc., etc., and then plus dot, dot, dot. Now, the cool thing about being able to write this general term, which you're going to have to be good at, is you can now write the series. I'm simply going to take this as n goes from 1 to infinity of 1 over 2 to the n minus 1. Now, I could also write this, if you think about this, and I promised this earlier, I can rewrite this instead of starting at 0, or excuse me, instead of starting at 1, I can start at 0, right? Couldn't I? Now think about what would happen. If I start at 0 and go to infinity, then instead of my first term being 1/2 to the 1 minus 1, which is 0, I would simply get 1/2 to the 0. Now I say this over and over and over again to kids. If you don't believe yourself, whoops, to the 0, try that again, sorry, to the n. I think I said n and wrote 0, but if I said 0, you can, what the heck, sorry you guys, my eraser's not working. Come on. Oh, you got to be kidding me. All right, try this again. Sorry guys. This is where technology fails. And we got a winner. Sorry about that. So this is 1/2 to the n. If you don't believe yourself, this stuff takes practice. You got to kind of wrap your brain around it. If you don't believe yourself, write out the first few terms and see if they're the same thing. You know what I'm saying? So when I'm looking at a series written in series notation, and I want to make sure that it equals a series where I'm looking at it sort of stretched out, then just write your first few terms. Well, 1/2 to the 0 is 1, plus 1/2 to the 1 is a half, plus 1/2 squared is 1/4. Sweet. I got the right thing. Now, let's get back to what we talked about pre-calculus. You've seen this before, right? This is 1 plus a half plus a fourth plus an eighth. Well, we learned back in pre-calculus that 1 plus a half plus a fourth plus 1/8 plus dot, dot, dot is equal to 2. Because 1/2 plus 1/4 plus 1/8 plus 1/16 is equal to 1. You can actually do it with a piece of paper. I'll show you guys in class later. This is an example of what kind of series. Well, it's geometric. But before we get to that, before we specifically define what a geometric series is it obvious that this converges? It converges because, if you think about it, if I take the limit as n goes to infinity of s sub n, which in this case equals 2, it will converge if, let's write this up, if I have a series as n goes from 1 or wherever to infinity of a sub n, if I take the limit as n goes to infinity of s sub n, and this either does not exist, this equals either does not exist, or plus or minus infinity, then we have a divergent series. And you'll see a lot of those. I'll do one of those in this lecture. But let's get back to what I like to call cornerstone or home base, and that is the geometric series. Geometric series. Now, I proved this in pre-calculus. There's a proof of it in your book as well, what I'm about to show you. Let's define the geometric series and when it converges. And then we'll talk about the proof. I'm not going to prove it again because, like I said, I already proved it in pre-calculus. And you can look in the book if you don't believe me. All right? A geometric series is defined as the series, typically in home position, think of it that way, as the sum as n goes from 1 to infinity of a times r to the n minus 1. Now, I won't always write it like that. I only write it like that when it suits me. That's the cool thing about series is you can write them how you want. I can also go from n equals 0 to infinity of a sub or a times r to the n. Now, notice what we get. If I list, it doesn't matter which one we use. I like to use this one. It makes more sense to me. Okay? Excuse me. If I just start listing terms, when n is 0, this r to the n is 1, right? A times 1 is a, plus, well, when n is 1, this is r to the first, so a times r to the first. This is ar, plus ar squared, plus ar cubed, plus dot, 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 plus ar to the n. Now, we got to be careful. Notice, it's ar to the n if I use this guy. It's ar to the n minus 1 if I use this guy here. So you got to be careful. You really do have to orient yourself. All right? I mean, it really doesn't matter which way you choose it, but it's where you start it that affects that first term. All right? Now, if you remember, r is called common ratio. Common ratio. And if you notice, if you think about the one from the previous page, remember the 1 plus 1/2 plus 1/4 plus 1/8. Well, all I did was multiply by a half to get the next term, multiply by a half to get the following term, etc., etc. That's called the geometric series. Now we know that geometric series, again from pre-calculus, or we can go over it in the book if you need to. Geometric series converge when the absolute value of r is less than 1, which implies that r is between -1 and 1. And moreover, that's the coolest part, is moreover, they converge to, let's see what you remember, a over 1 minus r.